Volatile Pulsar reveals millisecond missing link. For the first time, astronomers have caught a pulsar in a crucial transitional phase that explains the origin of the mysterious millisecond pulsars. These pulsars spin much faster than expected for their old age, and astronomers believe their rotation receives a boost as they accrete matter in a binary system. The newly found pulsar swings back and forth between accretion-powered X-ray emission and rotation-driven radio emission, bringing conclusive evidence for their rejuvenation. The discovery was made possible by the coordinated efforts of ESA's two missions that scan the high-energy sky, Integral and N.W.O. Pulsars are the highly magnetized, spinning remnants of massive stars and are primarily observed as pulsating sources of radio waves. The radio emission is powered by the rotating magnetic field and focused in two beams stemming from the magnetic poles. As the pulsar rotates, the effect is similar to that of a rotating lighthouse beacon, resulting in distant observers seeing regular pulses of radio waves. The emission mechanism of pulsars transforms kinetic rotational energy into radiation, and as this energy is radiated over time, the rotation is slowed down. Whilst pulsars spin rapidly at birth, they tend to rotate more slowly, with periods of up to a few seconds, as they age. For this reason, astronomers in the 1980s were puzzled by the discovery of millisecond pulsars, old but extremely quickly rotating pulsars with periods of a few thousandths of a second. The mysterious millisecond pulsars are explained through a theoretical model known as the recycling scenario. If a pulsar is part of a binary system and is accreting matter from a stellar companion via an accretion disk, then it may also gain angular momentum. This process can rejuvenate old pulsars, boosting their rotation and making their periods as short as a few milliseconds. This scenario relied on the existence of accreting pulsars in binary systems, which can be detected through the X-rays emitted in the accretion process. The discovery of millisecond pulsars in X-ray bright, binary systems in the 1990s brought additional support to this model. But until early 2013, astronomers had not found conclusive evidence of a direct link between X-ray bright millisecond pulsars in binary systems and the radio-emitting millisecond pulsars which they had been investigating since the 1980s. With our discovery of a millisecond pulsar that, within only a few weeks, switched from being accretion-powered and X-ray bright to rotation-powered and bright in radio waves, the search is finally over, says Alessandro Papito from the Instituto Ciències de l'Espai, ICE/CSIC, in Barcelona, Spain. Papito led the team of astronomers that detected this key source, which is located in the globular cluster M28. Their results are published in Nature. With its twofold behavior, this millisecond pulsar has a similar role to that of the platypus or the echidna in the animal world, which lay eggs but also produce milk to feed their offspring, a living evolutionary link between reptiles and the mammals, he adds. The new discovery is based on a fruitful synergy between the ESA's two missions probing the high-energy universe, Integral and N.W.O. But it wasn't until we compared the spin period and the orbital parameters of this object to those of other known pulsars belonging to the same globular cluster and listed in astronomical catalogues, that we noticed something peculiar must be going on, says Papito. The astronomers realized that the numbers matched perfectly those of another pulsar that was detected a few years ago, but at radio wavelengths, not in X-rays. The only available observations of this pulsar were published in a graduate thesis in 2006. Nobody had conducted follow-up observations of that radio pulsar, because it did not seem in any way interesting at the time. It appeared to be just another millisecond radio pulsar, notes Papito. But when he compared it to a pulsar, We realized immediately that this source, which had once been bright in radio waves and was now shining in X-rays, was no ordinary pulsar. The astronomers kept monitoring it with X-ray telescopes but also started a series of radio observations. They thought that, sooner or later, the pulsar might change behavior again and switch back to being bright in radio waves. What we didn't expect was that this would happen within a few weeks, comments Papito. The pulsar, which had been first detected on the 28th of March 2013, was bright in X-rays for the entire month of April. Then, as its X-ray emission started to decline, radio waves were detected as soon as early May. It was a stroke of luck that the pulsar changed its behavior on such a short time scale, comments Botso. But it wasn't just good fortune. The synergy between all the observatories involved in this study, and in particular the complementarity of Integral's large field of view and Newton's great sensitivity, was crucial for us to detect and correctly identify this object in time. Not only did these observations prove the evolutionary link between accretion-powered, X-ray bright millisecond pulsars and their rotation-driven, radio bright counterparts, as predicted by the recycling scenario. The data also showed that during this evolutionary process, which may last several hundreds of millions of years overall, the pulsars go through an intermediate phase that involves swinging back and forth between the two states several times, emitting alternately X-rays and radio waves, until finally becoming purely rotation-powered, radio-emitting millisecond pulsars. The astronomers ran a background check on archival data from NASA's Chandra X-ray Observatory, and found that the same source was also bright in X-ray in 2008, and they expect it will flip back again in the next few years. This bouncing behavior is caused by a rhythmical interplay between the pulsar's magnetic field and the pressure of accreted matter. When accretion is more intense, the high density of accreted matter inhibits the acceleration of particles that cause radio emission. So the pulsar is not visible in radio waves but only through the X-rays radiated by the accreted matter. When the accretion rate decreases, the magnetosphere expands and pushes matter away from the pulsar. As a consequence, the X-ray emission becomes weaker and weaker, while the radio emission intensifies. The discovery of this transitional pulsar completes a quest that has gone on for a couple of decades, comments Eric Kaalkes, Integral Project Scientist at ESA. In spite of the long time required for this detection, we believe that pulsars in such binary systems are fairly common, so we're looking forward to finding more, concludes Norbert Schkartl, Newton Project Scientist at ESA. Background information. The results described in this article are reported by A. Papito and colleagues in the paper Swings Between Rotation and Accretion Power in a Binary Millisecond Pulsar, published in Nature, 501, 517, 520, the 26th of September 2013. The study is based on data from a number of spaceborne, high-energy observatories, as well as ground-based radio telescopes. The source IGRJ 18245-2452 was first detected as an X-ray transient with the wide-field IBIS/ISGRI imager on board ESA's Integral mission on the 28th of March 2013. Subsequent observations with ESA's Newton and the X-ray telescope, XRT, on board NASA's SWIFT mission confirmed that this source is a millisecond pulsar with a period of 3.93185 milliseconds. The X-ray outburst activity is caused by the pulsar as it accretes mass from its companion, a low-mass star with a mass around 0.2 times that of the Sun. This millisecond pulsar is located in the globular cluster M28, at a distance of about 18,000 light-years from Earth. Comparison with data from other pulsars allowed the astronomers to identify IGRJ 18245-2452 with another object that had been observed in the past, the rotation-powered, radio-emitting pulsar PSRJ 1824-2452I. The properties of this pulsar were reported in the graduate thesis of Steve Begin, completed at the University of British Columbia, Canada, in 2006. Additional X-ray observations were performed with NASA's Chandra X-ray Observatory in April 2013. Archival data from Chandra of the same field, dating back to 2002, 2006 and 2008, were also available, showing that this pulsar had exhibited variable behavior in X-rays also in the past. The pulsar has been also monitored in radio waves using the Australia Telescope Compact Array, the Green Bank Telescope, the Parkes Radio Telescope, and the Westerbork Synthesis Radio Telescope, from April 2013 onwards. The pulsar became active at radio wavelengths again on the 2nd of May 2013. The International Gamma Ray Astrophysics Laboratory, Integral, was launched on the 17th of October 2002. It is an ESA project with the Instruments and a Science Data Center funded by ESA member states, especially the principal investigator countries, Denmark, France, Germany, Italy, Spain, Switzerland, and Poland, and with the participation of Russia and the USA. The mission is dedicated to the fine spectroscopy, E/E=500, and fine imaging, angular resolution, 12 Arcman FWHM, of celestial gamma-ray sources in the energy range 15 kV to 10 MeV with concurrent source monitoring in the X-ray, 4 to 35 kV, and optical, V-band, 550 nanometers, energy ranges. The European Space Agency's X-ray Multimirror mission, XMM-Newton, was launched in December 1999. It is the biggest scientific satellite to have been built in Europe and uses over 170 wafer-thin cylindrical mirrors spread over 3 high-throughput X-ray telescopes. Its mirrors are among the most powerful ever developed. XMM-Newton's orbit takes it almost a third of the way to the Moon, allowing for long, uninterrupted views of celestial objects.